Welcome back to SDL2 plus OpenGL shaders mini-series where we learn real GPU programming in pure C. So for this log, we're unlocking one of the most powerful tools in graphics programming, which is the transformation matrices. So you'll learn how to apply the model, view, and projection matrices. So the MVP pipeline to move, scale, and rotate the object in 2D and 3D space. And yes, you'll write our own matrix math in C, build a MVP system from scratch, and make this colorful triangle rotate smoothly using the shader uniforms. So grab your code editor, open up your previous project, and let's dive into the world of transformation matrices and OpenGL. Now for the project structure, we have the CMake-list.txt, shader folder, and src folder. So inside the src folder, we have the main.c, render.c, and render.h. And also we have a shader_utils.c and shader_utils.h. So inside the shader folder, we have the fragment.glsl and vertex.glsl. Now we have a CMake file or CMake-list.txt file. So this is the CMake configuration. So CMake will generate the executable file, and it will be the responsible for linking the libraries and the assets. Now for our render header file, we will going to have an include guards and the includes directives. So we have a macro, or the constant that we need, which are the m_pi. So that is our value for our pi. And also we have our constant window width and window_height. So here we have a function prototype. So we have a render function. So it will going to have a shader program, a vertex array object, and angle. And lastly, we're going to end our include guard. Now for the render.c file, we're going to include our render.h file or render header file. Now in line 6 up to 15, we will going to have a helper function. So it is a 4x4 matrix multiplier. So the name of that helper function is mat4_mul. This function multiplies two 4x4 matrices, so it represents as 1D arrays and stores the results in the result matrix. It iterates through each row of matrix A and each column of matrix B to compute the dot product of each element in the resulting matrix. So this matrix multiply or multiplications is necessary to combine transformations like rotation, translation, and projection into a final transformation matrix. So now we have our render function. So the render function is the function that handles the rendering of the scene. So the shader program, a compiled OpenGL shader program. So it used to run the GPU code for the rendering. So the vertex array object, a reference to an OpenGL vertex array object, which store the vertex data for the object being drawn to the screen. So here we have also the angle by which the object, likely a triangle, would be rotating during the rendering. Now for the line 19 up to 20, this line will set the clear color and clear the screen. So the GL clear color set the color that will be used to clear the screen. So in this case, a dark shade of blue. So GL clear, we have a GL underscore color underscore buffer underscore bit. So it clears the color buffer. So the part of the memory that holds the pixel data to the display. So effectively wiping the screen before the new frame is drawn. So in line 22, we have the GL use program function. So this activates the specific shader program, which is the shader program. So here it will going to tell the OpenGL to use the shader for any subsequent rendering operation. Now we're going to have the essential for transforming our 3D space. So we are going to have our aspect ratio of the window. Now we have the radians, so the angle is converted from degrees to radians because of the OpenGL, and most math functions use radians. That's why we convert that. So here for the matrix model or the rotation, so this matrix represents a rotation transformation around the Z axis. So the rotation matrix for a 2D object in 3D space, in this case a triangle. So a cos A and sine A are the sine and cosine. Cos A and sine A are the cosine and sine of the rotation angle respectively. So the matrix is constructed such that when multiplied with the vertex, it rotates the vertex by the specified angle around the z-axis. So we have the matrix identity. So here we were going to have our view. So we're going to have a view matrix, so it will going to represent the camera transformation. So if in any case it sets to the identity matrix, now we're going to have a view matrix, so this represents the camera transformation. So in this case it set the identity matrix, and meaning there's no camera transformation, so the camera is placed at the origin looking down the z-axis. If there are a camera transformation, this matrix would translate and rotate the scene to simulate the movement of the camera. So we have a projection matrix. So the projection matrix defines how the 3D coordinates are projected onto the 2D scenes. So this particularly matrix is an orthographic projection, which is a type of projection where the object remains the same size regardless of their depth. The matrix scales the x-axis by one float divided by the aspect ratio to account for the aspect ratio, ensuring that the scene isn't stretched or squeezed. Now we're going to combine the matrices. So we will going to have the BP, or the model view projection. So this line will combine the model, view, and projection matrices into the final formation of our matrix, which is the MVP. So first, the view and the model matrices are multiplied to get the model view matrix, which is the MV. And then lastly, we're going to the projection matrix is multiplied by the MV to get the final model view projection, or MVP matrix, which will transform the vertices from object space to screen space. Now in line 60 to 61, we will going to have the MVP block or MVP location. So here we will going to send the MVP matrix to the shaders as a uniform variable. So the GL uniform location gets the location of the MVP uniform in the shader program. So the GL uniform matrix for FB sends the MVP matrix to the shader, and it tells the shader how to transform the vertices using these matrices or using the matrix. Now in line 63 up to 67, so this line of code, it will going to render the triangle. So in line 64, it will going to bind the vertex array object, which holds the vertex data for the triangle. So in line 65, it will going to draw the triangle. It tells the OpenGL to draw 3 vertices, which is the triangle vertices from the bound vertex array object. Also in line 66, it will going to unbind the vertex array object after rendering. Now for the shader header file, we're going to have an include card and include directives. So we have a function prototype called load_shaders. Now in line 7 up to 14, we're going to have our helper function. This helper function called read_file. It will going to open a file at a given path for reading in a binary mode or RV. So if the files cannot be opened, it prints an error message and return null. And then if it's successful, it prints a success message indicating the shader file has been read. So in line 16 up to 18, this line determines the size of the file. And also we're going to have a rewind, so it moves the file pointer back to the beginning to prepare for reading. So in line 20 up to 27, this allocates memories to hold the file contents, so including an extra byte for a null terminator like /0. Now in line 29 to 31, we're going to read the file content into the buffer and adds a null terminator at the end of the buffer to make it valid C string, and then we're going to close the file after the reading. And lastly, in line 32, we're going to return the buffer containing the shader source code. So here for the load_shaders function, so this is the main function that loads, compiles, and links the vertex and fragment shaders into the OpenGL program or OpenGL shader program. So it takes 2 parameters, the path of the vertex shader and the fragment shader source code files. So in line 36 to 37, we're going to have a function call, which are the read_file function to read the source code of both the vertex and the fragment shaders into the vertex_code and fragment_code. And then if either the vertex or the fragment shader source code could not be read, it prints an error message and returns 0. So it indicates failure. So if both shaders are successfully read, so it prints a success message. So in line 45 up to 49, we're going to create a new vertex shader object. So we're going to set the source code of the shader object, and it takes the vertex_code read from the file and compiles the vertex shaders. Now in line 50 up to 58, we're going to check whether the vertex shaders has compiled successfully. If not, it retrieves and prints the compilation error using the GL gets shader info log. So if the compilation is successful, it prints success message. Now in line 60 up to 65, similar to the vertex shader, this part creates the fragment shader object and loads the source code from the fragment_code and compile it. So if we're going to check if the fragment shader compiled successfully, and if it not, it retrieves and prints the error. If the compilation is successful, it prints a success message. Now we're going to have shader linking program. So in line 74 up to 77, it creates an OpenGL program object, and also it will going to attach the compile vertex and fragment shaders to the program, and then we're going to link the shaders together into a single shader program. Now in lines 79 up to 86, we're going to check if the shader program was linked successfully. If the link fails, it prints the error message, and then if the linking is successful, it prints a success message. Now in 89 up to 92, after linking the shaders into the program, the individual shaders objects are no longer needed. So they are deleted using the GL delete shader function. And then the memory allocated for the shader source code, which are the vertex underscore code and the fragment underscore code, is freed as well. And lastly, we're going to return the shader program ID, so which is ready to be used for rendering. Now inside the main.c file, we include our directives, and then we initialize our SDL, and then we set up our OpenGL, then we load the shaders, and if it's successful, we will going to print a success message, and also if it's not or there is an error, we're going to print out a message. So here the GL use program function, we're going to tell the OpenGL to use the loaded shaded program for a subsequent rendering. So here we set up the vertices. We're going to set up the triangle vertices in line 37 up to 41. So in line 43 up to 46, we have our vertex array object and the vertex buffer object. So we're going to store the state about vertex attributes, and also the vertex buffer object stores the actual vertex data into GPU memory. In line 48 up to 50, we're going to bind the vertex array object and vertex buffer object. Now we're going to bind the vertex array object and the vertex buffer objects for the rendering. And lastly, we're going to upload the triangle vertex data to the GPU. Now in line 52 up to 55, we set up the vertex attributes. So the attribute 0 is the position data, so which has the first 3 floats, and we have a attribute 1, we have a color data next, which is 3 floats as well. Now in line 57 up to 62, we set up the MVP matrix, which are the model view projection. So if the MVP or model view projections matrix uniform locations in the shader program, the MVP matrix is used for transforming the object in 3D space. If the uniform is not found, we're going to print the error message, and if it's not, we're going to print a successful message like OK uniform MVP. Now we're going to have our main loop. So in line 75, we're going to increment the angle by 0.5 float on each frame. So it will going to cause the triangle to rotate slowly. Well, it's not that slow, but it will going to rotate. So here we have our render function. So it called to draw the triangle with the updated rotation based on the angle. And lastly, we're going to clean up our resources using the cleanup function. Now we're going to compile our project or build our project using the same make configuration that we made before. And then the same make will generate the executable file under the bin folder, and then we're going to execute that executable file. And that's it for this log. Your triangle is now alive and moving with math. In this video, you'll learn how to build your own 4x4 matrix system in C, apply translation, scaling, and rotation. Pass an MBP uniform to your shaders for real-time transformation. So in the next log, I think we'll have a texture mapping plus shaders effects. So we'll load image, map them onto geometry, and combine texture with custom fragment shaders. If this video helped you, hit like and subscribe. Thanks for watching and see you in the next one.